The first quarter-century of exoplanet science was dominated by discovery. The confirmation of planets around a pulsar in 1992, the detection of the hot Jupiter 51 Pegasi b in 1995, and the great harvest of thousands of transiting planets by NASA Kepler mission, which together established beyond any doubt that planets are common. The field has since matured into something different, a population science, whose object is no longer the individual planet but the statistical distribution of planets across mass, radius, orbital distance, and type of host star, the demographics of planetary systems as a whole. By September of 2025, the running tally stood at 6,000 confirmed planets, with more than 8,000 further candidates still awaiting confirmation. The task of this chapter is to read that population, and to distinguish what it firmly tells us from the questions it leaves genuinely open. The raw catalogue, however, is a badly biased sample of the true population, because each detection method sees only the slice of nature its physics is sensitive to. The transit method, which found the great majority of known planets, favors large planets on short orbits, while the wobble method favors massive, close-in ones, so the catalogue's apparent makeup reflects those selection effects at least as much as it reflects reality. Converting a biased catalogue into an unbiased occurrence rate is therefore the foundational problem of the whole enterprise. The procedure is to measure a survey's completeness empirically by injecting huge numbers of artificial planet signals into the real data and recovering them through the identical detection pipeline, which builds a map of detection efficiency across the plane of radius and period. The occurrence rate in any bin is then the number of planets found there, divided by the number of stars searched times the completeness, so that each detected planet stands in for all the similar ones the survey would have missed. The central results that emerge from this careful accounting are both robust and surprising. Small planets are far more common than large ones, and the frequency rises as one looks toward smaller sizes, toward longer periods, and toward smaller host stars, so that sub-Neptunes are roughly 3 times as common around red dwarfs as around sun-like stars. Above all, the single most common kind of planet in the galaxy turns out to be a kind entirely absent from our own solar system. These are the super-Earths and the mini-Neptunes, worlds intermediate in size between Earth and Neptune, and they occur around a large fraction of all stars, yet our own system jumps straight from the Earth to a Neptune, nearly 4 times its radius with nothing whatever in between. The commonest planets in the universe are ones we had no local example of at all. A useful way to orient oneself is the diagram that plots every detected planet by its mass and its orbital period, on which the detection methods carve out overlapping territories and the population reveals real overdensities and voids. At large sizes and short periods sit the hot Jupiters, giant planets on orbits of only a few days, which are intrinsically rare, circling only about one sun-like star in 100, yet whose enormous signals made them the easiest planets to find, and so left them heavily overrepresented in the early catalogues. At small sizes lies the dominant population by sheer number, the super-Earths and sub-Neptunes, and these are frequently arranged in compact systems of several small planets packed together inside an orbit smaller than Mercury's, a tightly spaced architecture with no counterpart anywhere in our own system. Between and around these populations lie 2 striking voids. The first is the Radius Valley, a marked scarcity of close-in planets with radii near 1 4/5 that of Earth, a gap that cleanly separates the rocky super-Earths below it from the envelope-wrapped sub-Neptunes above. The second is the hot Neptune Desert, a deficit of Neptune-mass, Neptune-sized planets at the very shortest periods of only a few days. The desert is widely read as the fingerprint of atmospheric escape. A planet of intermediate mass at such extreme irradiation is heavy enough to have gathered a hydrogen and helium envelope, but not heavy enough gravitationally to hold onto it against the fierce high-energy radiation it receives so close to its star, so its envelope is boiled away, and it is either stripped to a bare core or destroyed. The edges of the desert are thus a fossil record of the contest between gravity and starlight. 2 further regularities organize this landscape. The chance that a star hosts a giant planet climbs steeply with the star's metallicity, its abundance of elements heavier than helium, a relationship naturally explained by the core accretion theory of planet formation, in which metal-rich disks build solid planetary cores faster, and so reach the threshold for runaway gas capture before the gas disk disperses. This correlation is strongest for the giants, and weak or absent for the small planets which seem to form readily almost regardless of a star's chemistry. And within a single compact system, adjacent small planets tend to be remarkably alike in size and evenly spaced in period, the so-called pisinapod pattern, often sitting near simple whole number period ratios, the signature of a past epoch of disk migration that swept the planets into resonant chains. That uniformity implies the dominant influence on a planet's character is the disk it grew in, more than the star it grew around. The hot Jupiters, though a minor population, deserve close attention as the planets that open the field and remain its best-studied laboratories. They are gas giants, comparable in mass to Jupiter and Saturn, orbiting in only a few days, most commonly around 3, at roughly a 20th of the Earth-Sun distance. 51 Pegasi b, the first found around a Sun-like star, is about half the mass of Jupiter on a 4-day orbit, 8 times closer to its star than Mercury is to ours. Such a thing was wholly unanticipated, for the solar system's own giants all lie far out beyond the snow line, and the reigning theory held that gas giants must form there, where ice supplies the solid material to build their cores, and must stay there. A Jupiter whipping around its star in days demanded an explanation for how it had arrived so improbably close. The demographic fact to hold onto is that hot Jupiters are rare, hosted by only about 1 in every 100 Sun-like stars, so that despite dominating the first decade of discovery, they are vastly outnumbered by the small planets, and their occurrence correlates with stellar metallicity more strongly than that of any other class. 2 broad theories explain how they reach their scorching orbits, and the evidence suggests both operate. In disk migration, the young giant trades angular momentum with the surrounding gas disk and spirals smoothly inward while the disk still exists, which should leave it on a near-circular orbit well aligned with the star's spin. In high-eccentricity migration, a violent dynamical event, a scattering off another planet, or a slow gravitational cycle driven by a distant companion, flings the giant onto a stretched, tilted orbit, whose close approaches are then ground down and circularized by tides. The 2 pathways make a clean, testable prediction about the angle between a planet's orbit and its star's spin, which can be measured from a subtle distortion of the star's spectrum as the planet crosses first the approaching and then the receding half of the rotating disk. The observed pattern points to a major role for the violent route. Hotter stars, which lack the deep churning envelopes that would tidally drag a planet back into alignment, are frequently found hosting hot Jupiters on badly misaligned, even backward orbits, whereas cooler stars, whose convective envelopes do realign them, show mostly tidy aligned systems, their earlier misalignments quietly erased. And some hot Jupiters are being slowly devoured outright, their orbits measurably shrinking as the tides they raise on their stars drain away their angular momentum, so that they must eventually spiral in and be torn apart. Beyond their dynamics, the hot Jupiters are the proving ground for the physics of fiercely irradiated atmospheres, and they present a defining, still unsolved puzzle. The natural measure of their heating is the equilibrium temperature, the temperature a planet would settle at if it simply re-radiated all the starlight it absorbs, which depends on the star's temperature, the planet's distance, how much light it reflects, and how efficiently its winds spread heat from day to night. Hot Jupiters run typically between 1,000 and 2,500 Kelvin, and the most extreme, the so-called ultra-hot Jupiters, exceed 3,000, hot enough to tear molecular hydrogen apart on their daysides, and even to boil rock and metal into vapor. This intense heating drives the puzzle known as the radius inflation problem. An old, isolated gas giant, left to cool and contract over billions of years, should end up with a radius close to Jupiter's. Yet a large fraction of hot Jupiters are grossly swollen, 1.5 to 2 times Jupiter's radius, the extreme case of the planet WASP-17b reaching about twice Jupiter's radius and ranking among the largest and least dense worlds known. Crucially, the degree of this inflation tracks the incident starlight. Planets cooler than about 1,000 Kelvin are not inflated, while above that threshold their radii swell systematically with irradiation. Something is clearly linking the stellar heating to the planet's deep interior, but what remains genuinely debated? The leading idea is that the thermal ionization of trace metals like sodium and potassium makes the hot atmosphere weakly electrically conducting, so that winds dragging this charged gas across the planet's magnetic field drive electric currents whose resistive heating penetrates to the deep interior. The stubborn difficulty is that the required extra heating is only about 1% of the intercepted starlight, yet it must somehow be delivered hundreds of kilometers down, and no single mechanism yet reproduces the whole population, which keeps hot Jupiter structure a live problem in planetary physics. Turning to the small planets that dominate the population, their most important feature is that they are not a single family but two. The decisive evidence came from a survey that measured the radii of small, close-in planets with unprecedented precision, using high-quality measurements of their host stars. The distribution of radii, instead of being smooth, showed two distinct peaks, one near 1⅓ Earth radii and another near 2 2/5, separated by a deep and narrow deficit, the radius valley itself, at radii between about 1½ and 2 Earth radii. This split appears only when the radii are measured sharply enough, and it partitions the small planet population into two physically different classes. Below the valley lie the super-Earths, planets of roughly 1 to 1½ Earth radii whose densities, where they can be measured, match a rocky iron and silicate composition like the Earth's own. Above the valley lie the sub-Neptunes, planets of 2 to 3½ Earth radii whose lower densities demand a substantial light component, either a hydrogen and helium envelope amounting to only a few % of the planet's mass wrapped around a rocky core, or else a water-rich, steamy interior. The reason a mere few % envelope makes such a difference is that the low-density gas, though it carries almost none of the mass, occupies an enormous volume, so that adding a thin skin of it is enough to lift a planet clean across the valley from the lower peak to the upper. The valley is understood as the predicted signature of atmospheric mass loss, and two mechanisms compete to explain it. In photoevaporation, the host star's high-energy radiation, most ferocious in the first few 100 million years, heats and blows away the upper atmosphere of a close-in planet, so that worlds above a critical size keep their envelopes while smaller ones are stripped down to bare cores, hollowing out the middle of the distribution. In core-powered mass loss, the energy comes from within. The leftover heat of formation, stored in the rocky core, seeps outward over billions of years and drives the envelope off from below, needing no high-energy starlight at all. Both scenarios reproduce the valley only if the stripped cores are rocky rather than icy, which has been read as evidence that most close-in planets formed from dry, rocky material inside the ice line, and the two make subtly different predictions about how the valley shifts with orbital period and stellar mass, which is the main observational handle for telling them apart. The single most powerful tool for reading a planet's interior is its mean density, which follows immediately once both its mass, from the stellar wobble or from the mutual tugging within a system, and its radius from a transit are known. A planet of 1 Earth mass and 1 Earth radius has exactly Earth's density and must be rock and iron, whereas a planet with Neptune's radius but only a few Earth masses must be a puffed-up, volatile-rich world. Plotting every such planet on a diagram of mass against radius exposes the structure of the whole population, and it is read against theoretical curves of constant composition, each computed by integrating the equations that balance a self-gravitating sphere, using a laboratory-calibrated relationship between pressure and density for iron, for rock, for water-ice, or for hydrogen and helium. The standard reference curves include an Earth-like model of about 1/3 iron and 2/3 rock, a pure rock model, a pure iron model and water-rich worlds, and a planet's place among them constrains what it is made of, but a fundamental ambiguity limits the reading, because a single mass and radius can often be matched by more than one recipe, a rocky core under a thin veil of gas mimicking a larger, wetter world so that density bounds a planet's composition without ever fixing it uniquely. For solid planets, the relation between size and mass is roughly a gentle power law, with radius growing only as about the 1/4 power of mass, distinctly slower than the 1/3 it would follow at constant density, because a more massive planet squeezes itself harder under its own gravity, and so grows in size more reluctantly than in mass. At still greater masses, the behavior reverses entirely. For a gas giant, piling on more mass compresses the interior so effectively, through ordinary compression and the strange stiffness of degenerate matter, that the radius barely changes and can even shrink, so the whole Jovian family clusters near a single radius close to Jupiter's own regardless of mass. A widely used empirical model captures this entire span from tiny worlds up to small stars as a set of 4 regimes with different slopes: the rocky, the gas-rich Neptunian, the flat Jovian and the stellar, placing the boundary between solid and gas-rich worlds at around 2 Earth masses. Importantly, that model is probabilistic. It builds in a genuine scatter of radius at any fixed mass, reflecting the real diversity of compositions, and so returns a spread of plausible sizes rather than a single deceptive number. With planets counted, weighed, and sized, the frontier of the field has moved on to characterizing their atmospheres, which means teasing a faint, wavelength-dependent signal out of the blended light of a planet and its far brighter star. 3 techniques, almost powerful for planets that transit, dominate the work. In transmission spectroscopy, the atmosphere is caught in silhouette during a transit. A thin ring of starlight filters through the planet's day-night edge on its way to us, and at the wavelengths where atmospheric molecules absorb, that edge is effectively larger, and the transit correspondingly deeper, so the depth of the transit as a function of color traces out the spectrum of the air. The strength of these features is set by the atmosphere's scale height, which favors hot, low-gravity, hydrogen-rich planets around small stars. An Earth-like atmosphere, heavy and dense, and clinging to a high-gravity world, produces a signal smaller by orders of magnitude, which is exactly why characterizing a truly terrestrial atmosphere is so punishingly hard. In emission spectroscopy, the planet's own heat radiation is measured by watching the secondary eclipse, when the planet slips behind the star. Subtracting the star-alone light from the combined light just beforehand isolates the planet's dayside glow, whose spectrum reveals its temperature structure, showing molecular bands in absorption when the air cools with height, and tellingly, in emission when a hot upper layer inverts that gradient. And in phase curve observations, the system is watched continuously all the way around the orbit as the planet turns its differently lit faces toward and away from us, mapping the temperature difference between day and night, and from any sideways shift of the brightness peak, the winds that carry the heat, since a super-rotating equatorial jet blows the hottest spot east of the point directly beneath the star. The persistent complication across all 3 methods is cloud and haze, whose high-altitude particles mute the molecular features and can masquerade as a genuinely gas-poor atmosphere. The James Webb Space Telescope, working since 2022, has transformed this whole enterprise with its Great Mirror, its infrared reach, and its extraordinary stability. Its early observations of the hot Saturn mass planet WASP-39b delivered the first unambiguous detection of carbon dioxide in any exoplanet atmosphere, a clean absorption band caught at overwhelming significance, along with water, carbon monoxide, sodium, and, quite unexpectedly, sulphur dioxide. That sulphur dioxide was the first clear sign of photochemistry on another world, for it is not a gas the planet was born with but one manufactured on the spot as high-energy starlight drives chemical reactions high in the atmosphere, and taken together the abundances point to an atmosphere richly enriched in heavy elements during the planet's formation. The harder prize by far is the atmosphere of a rocky world, and here Webb's results have been sobering and valuable in equal measure. For the innermost of the 7 Earth-sized planets circling the nearby red dwarf TRAPPIST-1, careful measurement of its heat glow gave a dayside temperature consistent with a dark, airless body that simply soaks up starlight and re-radiates it from the dayside alone, with no winds to spread it and no detectable carbon dioxide, so the data favor a bare rock with little or no atmosphere at all. Observations of its neighbor tell the same story. These null results directly test whether rocky planets around active red dwarfs, whose harsh early radiation may strip their air away, can hold onto an atmosphere in the first place, a question central to the habitability of the most common stars in the galaxy. Webb and its predecessors have also watched atmospheric escape directly, first as excess hydrogen absorption during a hot Jupiter's transit, and now through a telltale helium signature that glows from hot, fleeing gas, Webb even tracing the long helium tail streaming off a warm Neptune, catching mass loss in the very act that sculpts the desert and the valley. The most contested result of all concerns the sub-Neptune K2-18b, a world in the habitable zone of a red dwarf, and the leading candidate for a so-called Hycean planet, a water ocean beneath a thick hydrogen sky. Webb detected methane and carbon dioxide there, and one team reported a tentative whiff of dimethyl sulfide, a molecule made on Earth chiefly by ocean life and therefore floated as a possible sign of biology, a claim now caught in an active and unresolved dispute, since independent reanalyses find the supposed feature sits down near the noise and can be matched just as well by other lifeless molecules. It stands as an open question, not a discovery, and as a sharp warning of how demanding the evidence must be before any spectral bump can be called a signature of life. The deepest open question of the field remains the frequency of genuinely Earth-like planets in the habitable zones of Sun-like stars, whose published estimates still span more than a factor of 10, precisely because that measurement lies where the survey corrections are largest and least certain. Our own solar system, once the only template we had for what a planetary system could be, now looks like just one architecture among many, and a somewhat unusual one at that, lacking both the super-Earths and sub-Neptunes that are the galaxy's commonest worlds and the compact, crowded-inner systems that encircle so many other stars. 2. Place our system in its true galactic context, and to learn at last whether worlds like the Earth are common or vanishingly rare, is the goal toward which this whole population science is patiently building.